97% of physicists believe SUSY could explain dark matter, yet no direct evidence exists. A 2022 survey by the American Physical Society found 89% of theorists consider SUSY a high priority despite lack of proof. But your body's every atom could be governed by the same math that SUSY predicts. In 1993, Leonard Susskind argued against Stephen Hawking's claim that information is lost in black holes, sparking a decades-long war over quantum gravity. The battle over SUSY's fate hinges on a single mind-bending equation that could rewrite the laws of physics as you know them. It took him 20 years to prove it. In 1971, deep within the Soviet Union's labyrinth of scientific secrecy, Yuri Golfand and Evgeny Likhnovsky scribbled equations that would reshape physics. Their paper, published in Teoretическая и математическая физика, proposed a radical symmetry. Every fermion had a bosonic partner, and vice versa. This wasn't just mathematics, it was a revolution. At the time, the USSR's theoretical physics community was a crucible of brilliance fueled by Cold War rivalry. Golfand, a physicist with a penchant for abstract thinking, and Likhnovsky, a mathematician obsessed with symmetry, worked in isolation, their ideas stifled by the regime's paranoia. Yet their work quietly seeped into the West, carried by defectors and smuggled journals. The concept of supersymmetry, or SUSY, was born, not in a particle accelerator, but in the margins of a Soviet textbook. By 1973, Julius Wess and Bruno Zumino would formalize it in Nuclear Physics B, but Golfand and Likhnovsky's 1971 paper remained the unsung origin. Their equations hinted at a universe where matter and force were two sides of the same coin, a vision that would haunt and inspire physicists for decades. The Cold War had forged more than weapons, it had forged ideas that would outlive empires. In 1973, Julius Wess and Bruno Zumino, working in the West, transformed SUSY from a cryptic Soviet idea into a mathematical language the world could speak. Their paper, Supersymmetry and the Classification of Representations, published in Nuclear Physics B, was a masterstroke of clarity. They introduced supersymmetric algebra, a framework where fermions and bosons were not just paired but mathematically entangled through operators that could raise or lower particle spins, like a quantum version of a ladder. This wasn't mere abstraction, it was a tool. Wess and Zumino also formalized superfields, mathematical objects that could encode both fermionic and bosonic particles in a single equation, a breakthrough that made SUSY tractable for particle physicists. Their work was a bridge, one end connected to the Soviet Union's 1971 breakthrough, the other to the Standard Model's rigid structure. In the West, where Cold War paranoia had long stifled Soviet science, Wess and Zumino's paper was a revelation. It was published in a journal with global reach, and within months, physicists in Europe and the US were debating its implications. The formalism was elegant, but its true power lay in its applicability. By 1974, theorists like Giuseppe Uhlig were already using Wess Zumino's tools to sketch the minimal supersymmetric Standard Model, a bold attempt to embed SUSY into the Standard Model's framework. This was no small feat. The Standard Model's equations were a labyrinth of forces and particles, and SUSY required doubling every known particle. Yet Uhlig and others saw opportunity. The hierarchy problem, the question of why the Higgs boson was so light, loomed large. SUSY, they argued, could stabilize the Higgs mass through cancellations between fermionic and bosonic contributions. Wess and Zumino's 1973 work wasn't just a theoretical flourish, it was the blueprint for a revolution. By the late 1970s, SUSY had become a lingua franca of particle physics, spoken from Geneva to Moscow, even as the LHC's proton beams remained decades away. By the 1980s, the minimal supersymmetric Standard Model emerged as the most ambitious attempt to integrate SUSY into the Standard Model's framework. Giuseppe Uhlig, working at CERN, spearheaded this effort alongside collaborators like Alan Darve and others, though Uhlig's name often faded into the collective shadow of the MSSM's development. The model proposed a staggering 120-plus supersymmetric partners for every Standard Model particle, Squarks for quarks, Sleptons for leptons, and a host of new Higgs bosons. This doubling of the particle zoo was not arbitrary, it was a calculated response to the hierarchy problem. The Higgs boson's mass, governed by quantum fluctuations, was unstable unless protected by a symmetry. SUSY, with its perfect cancellation between fermionic and bosonic contributions, offered that shield. The MSSM's elegance lay in its ability to stabilize the Higgs mass against radiative corrections, a feat that made it a darling of theoretical physicists, yet the model's predictive power was its double-edged sword. It required precise couplings and mass parameters, many of which were arbitrary. This led to a proliferation of SUSY models, each tweaking the MSSM's framework in slightly different ways, creating a labyrinth of possibilities. The LHC, which began operations in 2009, became the battleground for these ideas. With proton collisions reaching 14 TeV by 2023, the LHC's ATLAS and CMS experiments scoured collision data for signs of gluinos, neutralinos, or any SUSY partner. But the results were damning. By 2018, Run-2 data excluded SUSY models with gluino masses below 2.5 TeV at 95% confidence, a threshold that had once seemed within reach. The Higgs boson's discovery in 2012, with its 125 GeV mass, further complicated matters. Its properties, such as its coupling strengths, deviated from SUSY's predictions, casting doubt on the theory's viability. The MSSM, once a beacon of hope, now stood as a monument to a grand vision that had yet to find experimental validation. The 1980s marked a turning point as the MSSM crystallized into a concrete framework, its architects, most notably Gian Giuseppe Uhlig, pushing SUSY toward the edge of experimental testability. Uhlig, working at CERN, collaborated with a network of theorists to map out the 120-plus supersymmetric partners for every standard model particle, from Squarks and Sleptons to a cascade of Higgs bosons. The model's audacity lay in its claim to resolve the hierarchy problem by pairing every fermion with a boson. SUSY introduced a natural mechanism to cancel out the quantum fluctuations that threatened to destabilize the Higgs mass. This wasn't just a mathematical flourish, it was a gamble, betting that nature's symmetry could shield the Higgs from the vacuum's relentless pull. Yet the MSSM's predictive power was both its strength and its vulnerability. The model required precise parameters, many of which were arbitrary, leading to a proliferation of variants, each tweaking the framework in slightly different ways. When the LHC began operations in 2009, its proton collisions, reaching 14 TeV by 2023, became the ultimate arbiter of SUSY's fate. The experiments, particularly ATLAS and CMS, scoured collision data for signs of gluinos, neutralinos, or any of the MSSM's predicted particles, but the results were damning. By 2018, Run-2 data excluded SUSY models with gluino masses below 2.5 TeV at 95% confidence, a threshold once thought achievable. The Higgs boson's discovery in 2012, with its 125 GeV mass, delivered another blow. Its coupling strengths deviated from SUSY's predictions, further eroding the theory's credibility. The MSSM, once a beacon of hope, now stood as a monument to a grand vision unfulfilled. Yet the LHC's investment, $15 billion by 2023, with SUSY searches consuming 15% of resources, underscored the theory's lingering allure. Even as experimental evidence dwindled, SUSY's shadow loomed over dark matter research, where the neutralino remained a tantalizing candidate. The story of the MSSM was no longer one of triumph, but of a theory teetering on the edge of obsolescence, its legacy etched in the equations that once promised to unify the universe. The absence of direct experimental evidence for SUSY by 2023 marked a quiet but profound reckoning. The LHC's 2018 Run-2 data, which excluded gluino masses below 2.5 TeV at 95% confidence, became a stark reminder that nature does not always conform to elegant theories. Yet SUSY's legacy endures not as a confirmed truth, but as a crucible for the next generation of physics. The theory's collapse under experimental scrutiny did not extinguish its influence, it redirected it. Lisa Randall, for instance, pivoted to exploring extra dimensions and dark matter, her work on the Hidden Valley hypothesis, echoing SUSY's ambition to unify forces beyond the standard model. Even as SUSY faded from the forefront, its mathematical tools, superfields, supersymmetric algebra, remained embedded in string theory and beyond. The neutralino, once SUSY's most tantalizing dark matter candidate, persists in indirect searches. Experiments like Excludes and the Fermi Gamma Ray Space Telescope continue to probe its existence, though results remain inconclusive. Meanwhile, the MSSM's failure to predict the Higgs boson's 125 GeV mass, lighter than SUSY's radiative corrections suggested, highlighted the theory's fragility. Yet this fragility is also its gift. It forced physicists to confront the limits of symmetry as a guiding principle. Today, SUSY is taught not as a solution, but as a cautionary tale, a reminder that beauty in equations must be tempered by the universe's stubbornness. Its story is etched in the chalk dust of lecture halls, where students grapple with the tension between theoretical elegance and empirical reality. The LHC's $15 billion investment in SUSY searches, now a footnote in particle physics history, underscores a deeper truth. The pursuit of knowledge is as much about humility as it is about ambition. And so SUSY lingers, not as a discovery but as a question. What if the universe is not symmetric, but chaotic? What if the laws we seek are not unified but fragmented? The search for answers continues, but the path is no longer paved with supersymmetry.